Before we talk about limiting reactants, let's try and make a sandwich. When I'm making the sandwich, I will be using bread, slices of bread. I will be using slices of tomatoes. I would be using slices of cucumbers and also slices of cheese. And when I put these ingredients together, I will end up with sandwich. Now, in my sandwich, when I make this, my ideal sandwich would need two slices of bread. Just a second, excuse me. Um, my ideal sandwich would need two slices of bread, four slices of tomatoes, five slices of cucumbers, and two slices of cheese to make one sandwich. What does this remind you of? Exactly. This reminds us of a balanced reaction equation. Now let's say that I start out with this process of making sandwich, and I look in my pantry and I get all the ingredients out, and I then find out that I have a total of 8 slices of bread, 12 slices of tomatoes, 20 cucumber slices, and 10 cheese slices. If I'm going to follow this given recipe to make the sandwich that I would want to serve to my friends, and these are the amounts of each of the ingredients that I have, what is the maximum number of sandwiches that I can make following this recipe? Exactly, 3. Why is 3 the maximum number of sandwiches? Because as soon as 3 sandwiches are done, what will happen? We will run out of tomatoes. We won't have any more tomatoes left over. We would have used up all of our tomatoes. Would we have used up the other ingredients at this point? No, we will still have some left over of the other ingredients. We would have 2 slices of bread left over. We would have 5 slices of cucumbers left over and 4 slices of cheese left over. Can these be combined to make a sandwich? Of course, yes, you can combine these leftover ingredients, make a different sandwich, but then it will not be this sandwich. It will not be this process. It will be a completely different process for a completely different sandwich. Okay, so we are very specific to this one that we're talking about. Now, this reactant that is completely used up in the process before other reactants and therefore stops the reaction is called the limiting reactant. Limiting reactant controls the amount of maximum amount of product that we can get in a reaction. In other words, in this case, limiting reactant tomatoes is the one that is going to determine the maximum number of sandwiches that I can make following this recipe. The maximum number of sandwiches that I can make following this recipe given based on the limiting reactant, which is tomatoes, is called the theoretical yield. Just one second. Is called the theoretical yield. Theoretically, if everything goes as expected, based on the tomatoes controlling the maximum number of sandwiches that I can get, that it would theoretical yield would be 3. The other reactants that are not used up, the other reactants that are not contributing to the determination of maximum number of sandwiches I can get, the other reactants that are left over unused are called reactants in excess or excess reactants. So those will be in excess. Okay, so this is just a general idea of what a limiting reactant is when you relate it to a chemical process. A limiting reactant is the reactant that gets used up, gets consumed first in a process and therefore stops the reaction. The reaction stops at that point. The formation of that product or products stops at that point in time, and therefore it is the limiting reactant that controls the maximum amount of product that can be made in this particular reaction. The other reactants that are left over are called, those reactants are called, said to be in excess. So in our course of study, there'll be several times that you will need to determine the limiting reactant given a reaction. If, for example, here is a reaction where nitrogen dioxide reacts with water to produce nitric acid and nitrogen monoxide. Now, when we run this reaction and we use the said amounts of the reactants, nitrogen dioxide and water, the question is which of the two reactants is going to control the maximum quantity of the product that we can get? Okay, in other words, the limiting reactant. Now there are some very set steps that you can follow to determine that. Step number one, as in any reaction, as in any problem involving a reaction, you must use a balanced equation. In other words, this is a stoichiometry problem. So please pause the recording and go ahead and balance this equation. When you do so, you get 3NO2 plus 1H2O produces 2HNO3 plus 1NO. Next step after balancing is to select a product that you would like to work with. When we say a product, please be very careful. It is specifically what the product means, which is something that is created as a result of a chemical process. Now, it doesn't matter which product you select. No matter which product you select, you would still get the same reactant being the limiting reactant. However, in future sessions, I might actually suggest that you select a certain product for the next steps because it's more convenient. That's the only reason, because by selecting that product, you might have fewer steps to work through. Okay, so let's select a product in this case, and randomly I'm selecting nitric acid. There is no reason, it's just because. The next step after you've selected a product that you're going to work with is for you to calculate the number of moles of this selected product that we can get from each of the two reactants separately. In other words, we need to convert 125 grams of NO2 and 95.0 grams of water separately to number of moles of this selected product. At this point, please pause the recording and set up these problems and calculate those to number of moles of nitric acid. Okay, so the first, of course, grams of NO2 can be converted into moles of NO2 using molar mass of NO2. Moles of NO2 can then be converted into moles of nitric acid because that's the product we decided to work with. You don't have to, you could have used NO as well and you'll get the same answer. This gives us 1.811200464, which when rounded to three significant figures gives us 1.81 moles of nitric acid. Similarly, grams of water can be converted to moles of water using molar mass, and then using the coefficients in the balanced equation that can be converted to moles of nitric acid, and this gives us 10.54384018 moles of HNO3, which when rounded to three significant figures gives us 10.5 moles of HNO3. When calculated in this way, then the reactant that makes less amount of the product is the limiting reactant. So in this particular case, the limiting reactant, it would be NO2, because that is capable of making less amount of the product than water. Please remember, a limiting reactant is a reactant, not the product. And a product is a product, what is created as a result. Okay, let's try another problem of a similar kind. Here we are dealing with combustion of ethyl alcohol. First step, of course, as in any case, is for us to write a correctly balanced reaction equation. Please pause the recording while you do that. So C2H6O plus 3O2 gives us 2CO2 plus 3H2O. Now, given these amounts of the reactants that are used in the reaction, we have to determine the limiting reactant. Let's select a product. You could select water or carbon dioxide, doesn't matter. Let's select, I selected carbon dioxide. Once I've selected carbon dioxide to work with, now I need to convert 52.6 grams of ethyl alcohol into moles of CO2, and separately I have to convert 75.0 grams of oxygen to moles of the same selected product, CO2. Okay, so go ahead, please pause the recording while you complete this. So grams of CO2, C2860 can be converted into moles using molar mass. That converts into moles of CO2 using coefficients in the balanced equation. When you calculate this and round it to three significant figures based on the amounts given, we get 2.28 moles of CO2 from ethyl alcohol. Oxygen can be similarly converted into moles. Please remember it's O2 and not O, hence 32, not 16. And then this can be converted into moles of CO2, and we need the molar ratio from the coefficients. We get that. When you calculate this and round it to three significant figures, we get that. Based on these number of moles of the selected product that we can get from each of the reactants separately, we can say that in this case, oxygen gas is the limiting reactant because it will run out before the other one would in this process. Okay, so let's go on to the next problem. Once again, the reaction is given. Part 1 of the question says identify the limiting reactant. Please go ahead, pause the recording while you attempt this on your own. So the balanced reaction equation would be calcium carbonate plus 2HCl produces calcium chloride plus CO2 plus H2O. Once again, you have to calculate the number of moles of a selected product, and again it doesn't matter which one you select from each of the reactants. I'm going to select water, so we need to convert 28.4 grams of calcium carbonate into moles of water and convert 9.45 grams of hydrochloric acid into moles of water as well. Please pause the recording while you complete this. So that goes into moles using molar mass and using coefficients. That goes into moles of water, and this gives us, after rounding to three significant figures, similarly 9.45 grams of HCl, 1 mole of HCl, 36.46 grams of HCl, that's the molar mass, and then 1 mole of H2O from 2 moles of HCl from the balanced reaction equation. Calculated answer rounded to three significant figures gives us 0.130 moles of H2O. Based on these numbers, we can say that the limiting reactant in this case is HCl. Okay, now there is a second part to this question which is asking us to calculate the mass of the excess reactant that will be left unreacted. In other words, they want us to calculate the mass of excess reactant, which is calcium carbonate. So they want us to calculate the mass of unreacted unconsumed calcium carbonate in after the limiting reactant has been consumed and the reaction has stopped. That would basically equal the mass of calcium carbonate you started with, that is 28.4 grams, minus the mass of the calcium carbonate that did react in this reaction. Now, there are different ways of solving this problem. There are different ways you can set up and calculate the mass of reacted calcium carbonate. I'm only going to show you one, which is knowing that HCl is the limiting reactant, we can figure out the mass of reacted calcium carbonate by determining how much calcium carbonate would it take to completely use up HCl, because that is the limiting reactant. In other words, that converts grams of HCl to moles of HCl. And now instead of relating the moles of HCl to the selected product water, we can figure out the moles of calcium carbonate that it would take to completely react with those many moles of HCl using the balanced equation. And once you've done that, you can convert the moles of calcium carbonate that will react with HCl to grams of calcium carbonate. So when you carry out this calculation, basically what you're calculating is the mass of calcium carbonate that does react. Calculated answer gives us 12.9710710 grams, which rounded to three significant figures gives us 13.0 grams of calcium carbonate that does react. So therefore, mass of unreacted calcium carbonate therefore will equal the mass of calcium carbonate that we started with minus the mass of calcium carbonate that was consumed, gives us 15.4 grams of calcium carbonate that will be left over.